Saxon Algebra 1, lesson 53. This is part 2. We just did this lovely review of the rule of different facts about exponents. If you missed this part, it's in part 1. This is part 2. Thank you for being patient. Now let's get into the problems. Isn't it interesting that they call math computations, let's say, problems? That's kind of a negative vibe. I'm not gonna lie. We should call them math challenges, all right? I guess what I do, these are called examples, but problems, that's depressing. Who wants to do problems every day? It's what people always tell me about how, oh, I have all these problems at work. I'm like, dude, I teach math. You wanna talk about problems? Which usually gets at least a smile out of people. We all have problems, but man, math, and I'm not complaining, math students have to deal with way more problems than me. Okay, ready? It's big and ugly to copy this down. So take a deep breath, sigh if you want, and then we will simplify. Okay, there's more to the problem, but let me have you copy that much down first. What we see is a fraction, a rational expression, if you want to be fancy, top and bottom. It's got a number, it's got 3 different bases, and they each have an exponent. Okay. Technically, the 3 has an exponent too. It's got an invisible 1, right? We can put that 1 in anytime we want, because we know that that's true, right? I should have put that whole last page in a puffy cloud of knowledge. If you want to do that in your notes, please do. But that's all good stuff. Okay, so we can do that. We can fill in numbers or variables that are bases that do not have an exponent. We can always give them a 1. And as you'll see in just a minute, and you probably already know, that can come in quite handy. Now, the part that I didn't do yet on this problem is that there are parentheses around the whole thing like this. And then there is a -2. What are those parentheses doing? What those parentheses are doing is saying this -2, this raising to the -2 power, we want to do that to every part of that expression. We want to do it to every base. So, just to help you understand what I'm talking about, we're going to use the power rule, right? Which is that if you've got a base with an exponent and you're raising it to a higher power, you multiply those 2 things together, right? We're going to use that first, and this is the power rule, because we're going to use some other rules too. Maybe we're not in this problem. We'll see. We're going to have to multiply the exponents together for every single one of these bases. See how there's the 3 and the x and the y? We have to get each one of them, and then we have to do the denominator too. Okay, so every single base is going to be raised to the -2. So we're going to multiply whatever exponent already exists times the new exponent. That's why it's helpful to write in the 1, so that then I can write 3 to the 1 times -2. That becomes 3 to the -2. In these problems, by the way, we don't worry about simplifying the negative exponents. Just leave them be. It's fine. X -2 times -2 becomes x to the 4th. Y, see how I'm just going down the line and paying attention to each base one at a time? That will be to the -10. And then Z will be to the -8. That is our final answer. Now, we can simplify this a bit. Did John ask us to do this? I'm just looking to see. Negative exponents are not necessarily right or wrong. What John asked us to do is simplify the exponent that is a number and leave the exponents on the variables as is, right? We could simplify those as well, but in this problem, we're only simplifying the number. So we'll still have x to the 4th, y to the -10 on top, but this minus sign on the exponent, the base of 3, tells us to flip it down. So it'll be 3 squared in the downstairs, which is 9, and then we'll have z to the minus 8. That's what John shows as the answer. He only clears up the negative exponent on the actual number rather than the alpha variables. And there's no way that you would have known that. I interpreted the problem that way. When you're doing these problems in the homework, you can read and see if he says anything in the instructions about how he wants the answer to look. But then when you go to check the answer, you may find that his answer looks different than yours. And so that's one way that you can check, is see if he simplified his negative exponents, and maybe you haven't done that yet, all right? Use the solutions manual, again, as a tool, not just to copy the right answer, but to help guide your work toward the right answer, all right? One way to make sure you're doing that is that you should never be writing down when you're looking at the solutions manual. When you're looking at the solutions manual, you're only trying to understand what's happening. Then you set that aside, go back to the book and look at your problem, go back to your paper. Now you do the writing, but you don't write direct, you don't copy anything out of the solutions manual. You just look at it, figure it out, and go, oh, I see what he did. He simplified all the negative exponents, and I still have mine. Okay, I'll go back and do that. Shove your book away, and off you go, all right? It's very important that you use the solutions manual, but it's very important that you use it well. In college, which I know you may not be worrying about college just yet, but in college, most professors expect you to be able to teach yourself certain concepts. Now, I cover most of the concepts that I can for you. I cover everything that I can for you, but in the different problems, challenges, there are times when you have to figure it out for yourself, and it's very important that you build your ability, your skills at solving problems for yourself. And that's what the solutions manual helps you do. Okay, let's do another one. Ready? This one does not have a downstairs. It's just an expression without a denominator. Okay, once again, we have a number and then 3 letter bases, alpha variables. Some are negative, some are positive. This 2 doesn't have anything. I'm going to go ahead and put a 1 there because I want all my bases to have an exponent. In this case, it was the numeric character, the number, if you will, that did not have a 1 that we filled in, right? This was 3 to the 1. It can be the letters too. That's not the way it always has to work. That's just coincidence. Now we're raising this whole expression to the minus 5. All right, again, it's like a distribution. We want to make sure, because those parentheses are saying this whole thing goes to the minus 5, we have to be very careful to make sure we hit every base. Okay? And if you kind of train your eyes to see the bases, I know it's kind of a cluttery mess, but if you zoom in on the bases themselves, then you just make sure that every single one of those gets hit with that minus 5. All right, 2. 1 times minus 5 is minus 5. A, minus 2 times minus 5 is positive 10. B, positive 2 times negative 5 is negative 10. And then Z, minus 10 times minus 5 is positive 50. Look at how, look at how I spread this out so that everything's not crammed together and impossible to read. Look at how I make sure that my bases are bigger and my exponents are smaller. Now, I'm using 2 lines to write my numbers. You might feel, if you feel comfortable doing that, do it. It's so much easier when you can tell your exponents from your bases. But sometimes what happens is, let's just take the letters here. Sometimes students are writing and it gets so squishy that it ends up looking like this. That's not okay, because I can't tell very well that those are exponents. Okay, so don't do that. Make sure you get a clear, crisp distinction between your exponent and your base. I pointed to the wrong thing, your exponent and your base, all right? My daughter used to grade papers In college, she worked for her professor. She was an astronomy major, and she worked for one of the professors that taught like a basic astronomy class. The biggest reason her professor told her that students lose points is because you can't read their writing. Whoa, that kind of blows my mind. Make sure someone else can read your writing. Okay, just like last time, we're going to leave those negative exponents, but we're going to simplify this. What is 2 to the minus 5th? Well, if you've ever played that game on your phone, 2048, or your mom's phone, or wherever you play games, it's called 2048, and it's about powers of 2. I love it. Then you'll know this, but what we do is we just multiply 2 times itself 5 times. So 2, 4, 8, 16, 32. All right, so that is going to be 32. This minus sign sends it to the basement. So our final answer is going to be all that over 32. And I'm just checking to make sure that's the right answer. Yes. Okay, so in John's preference, John's choosing this, not us. And there's not necessarily an inherent logic to it. He's saying leave negative exponents on the variables, but simplify the numbers. C. This one, once again, the whole expression is inside the parentheses, and then we have a 2 up here. This one is tricky because look at all these letters and numbers that don't have exponents on them. And that can fry your brain when you go, wait, I know I'm supposed to multiply, but wait, times what? Remember, fill it in with ones, and then you'll have something to multiply it against. This then is equal to 4 squared times x squared times y squared over m, oh, I didn't draw my arrow, m to the minus 4. Beautiful. And then for our last step, we can multiply the number out, 16x squared y squared. See, that's a little small. You can't really read my letters very well, can you? Over m to the minus 4. So it goes wrong really fast. These are all right. I was checking them, but I didn't smiley face them. All right, and then our last one, D. And then we're going to switch topics after this. Again, giant parentheses. We'll talk about it later when the whole expression is not in parentheses. How do you handle that? We'll talk about that another day. This is all power rule, the most straightforward step where everything is being raised to that power. All right, so we're going to fill in with ones where we need to, 3 to the 1. Now this, x to the 0 power, what do we do with that? Well, remember, x to the 0 power equals 1, right? That's one of our rules I reviewed before. That means, and when you're multiplying something by 1, it doesn't change anything. So what we can do is we can just strike that out completely. That's why my name is Striker, because I like to strike things out. That's not true. But anyway, I'm just crossing that out. I can ignore the whole thing. I don't need it. I'll put a 1 there, and now I'm good to go. All right. Oh, I see what I did. This is actually E. John went to suddenly a column presentation. We will continue to do this when we'll go back and do D. There's a D and an F. Okay. This is all correct. Yeah, I just copied the wrong problem. I copied it correctly though. Okay, so here we go. We don't have to deal with that one anymore. So it'll be 3 to the 1 times 3 is 3. X to the 1 times 3 is 3, or I'm sorry, that's a Y. The x term is gone. Over k to the 3 times 4, that's 12. And then we can simplify this. 3 times 3 is 9. Times 1 more 3 is 27. Y to the 3rd over k to the 12th. All of that is correct. Okay, A, B, C, E. Let's go back and get D. Here's D. 3x y to minus 2 over p to the 5th. We're raising all of this to the minus 2. As you can see in these calculations, it doesn't really matter if it's negative or positive. We just make sure we keep track of that as we multiply. Fill in with ones. I don't always take the time to draw the arrowheads, but I always draw these, just like I do with distribution, to make sure I am paying attention to each one of those bases. It's easy to go fast and miss one. This will give me 3 to the minus 2, x to the minus 2, y to the positive 4, over p to the, oh wait, I didn't multiply it. I wrote the same thing down. Minus 10, right? And then, once again, we'll use John's rule of simplifying, fixing the number, but not the letter bases. Okay, 3 to the minus, that means it goes down. 3 squared is 9. So writing the full answer to this will be x to the minus 2, y to the 4th over 9 times p to the minus 10. Let's see if I got it right. X to the minus 2, y to the 4th, 9. Yes, that's right. All right, and now the final one is F. Are these getting harder? I think so, because they're getting trickier because we're throwing in concepts like x to the 0 equals 1. But for the most part, these problems aren't any harder or easier than one another. 2 to the 0 power. Oh, get excited whenever you see 0 as an exponent, because your problem just got a little shorter. Because you can just whack that out. Z. Remember that I put a slashy through my z's because my z's otherwise can look like my 2's. This is a loopy 2, so that one's safe, but sometimes I make my 2's without the loop, and then no one knows if it's a 2 or a z, and that's a bad look. Okay, just like any letter raised to the 0 power equals 1, this is true also for any number, right? It doesn't have to be a letter. It can be a number too. But as soon as we see that raised to the 0 power, we can just whack it out. Just strike it out. Think of me. You can do it. You don't, in some ways, you don't even have to write it down. So there's that. We're raising it, holy smokes, we're raising it to the 15th power. Now, I'm glad that we got rid of the number, because otherwise we would have to do 2 to the 15th power, which we could do. You just keep doubling it, right? But let's save ourselves the drama, shall we? Because we can happily cancel that out. Okay, now it's just a matter of multiplying by a big number, but we can do that. This z doesn't have an exponent. Let's give it a 1. Okay, so we'll have, that's gone. We'll have x to the minus 30, y to the, well, let's see, if 15 twice is 30, then 15 4 times would be 60, right? And it's positive, because that's positive, over z to the 15th. Yay! That's the right answer. Beautiful. Okay, that is the power rule. There's all the information we started with, right? Giant puffy cloud of knowledge around this. I won't take the time to draw it. These are all the different tools that we needed to do these problems. This is all information. You're becoming quite expert at exponents and these rules for exponents. We're going to use them a ton. So the more energy you put into memorizing, I mean, you probably already understand this part, but making sure you understand those simple rules and memorizing this chart, oh my gosh, it's going to save you so much wear and tear on your brain. Okay, let's now talk about our second topic, which is conversions of volume. I'll tell you what you already know about that. You know how to convert length. We use unit multipliers, And we use things like inches and feet and miles and centimeters and meters. And we're just converting length. We're working in one dimension. And when we do that, we use one unit multiplier. A unit multiplier, just to remind you, is a fraction that relates two different units that are of equal length. So one unit multiplier might be 1 foot over 12 inches or 12 inches over 1 foot, right? The unit multiplier is that fraction thing that we multiply by. When we're converting a length, we only have to use one unit multiplier. As opposed, and that's like a piece of string, right? That's the first kind. The second kind is when we're converting area, like a piece of paper or a piece of cloth. And that's called a conversion of area. And in that, we're converting in two dimensions, right? Because we have to convert this way, and we have to convert that way. In length, we only have to convert that way. So in area, we have two dimensions, so we have to use, dun, 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 two unit multipliers. And we can use the very same one, we just have to use it twice in order to do the calculation properly. Well, today we're talking about conversions of volume, and volume is fun because it's the three-dimensional cube. And I think I usually tell every class this story. I so remember the day in grade school that I learned how to do this, and I thought I was such a boss. I mean, I kind of was, right? Because it's cool to do that. You have to convert this dimension, and now this one. So guess what? That's a three-dimensional object, and so we have to use 3 unit multipliers to make these conversions. All right, let's practice that. How many examples do we have? 1, 2, just 2. All right, this, make sure goes deep into your brain. Copy it if you need, yeah, copy it for sure. This helps it all make sense. All the different rules we have kind of fit together into one cohesive idea. Okay, pause me if you don't have this, otherwise I'm going to go on to the problem. Okay, are you ready? Make sure my book is properly centered. Okay. Now, all of those problems we did before with the power rule, those were not technically examples. They were just the A, B, C, D, E, F. Isn't that weird? So now this becomes example 53.1. I don't know what to say about that. Okay, here's what John wants us to do. Use 3 unit multipliers to convert 180 cubic feet. And what I like to do is I like to write out feet 3 times. Cubic implies 3. A cube is 3 times. Because it has 3 dimensions. But I want to write them out because I want to be able to cancel them. And we want to convert it to cubic inches. So I'm going to go inches. I'm going to go down in this so I have a little more room to work. You could go down here just to make it easier to work. And John tells us you're going to multiply it by 3 unit multipliers. So I'm going to draw the space for my 3 unit multipliers. We're going to be doing this for a long time, and they're going to keep getting trickier and trickier. My advanced students today are learning a really complicated physics calculation about angular velocity that involves unit multipliers. So this, don't worry, you will use this, and it will get harder. So just make sure you use the framework that I use, and it'll always make sense to you. Okay, so we have to go from feet to inches. Can we do that in one step? Yeah, we can do that in one step. So in all 3 of these boxes, we're going to be going from feet to inches. So let's get those set up. Feet are on the top. That's our starting unit. So we know we want feet on the bottom. And I feel good about writing these 3 out because I see, oh, look, they're going to cancel, right? Now that tells me inches are going to be on the top because we want to go from feet to inches. Which is bigger, a foot? How many inches are in a foot? 12. Okay, remember we want the starting unit to be on the bottom because that will allow us to cancel. And I'm going to do that right now. And that's why I like to write these out separately so I can cancel each one. That leaves us with inches in our problem, and that's what we want in our answer. So I circle those and show, oh yeah, I got it just the way I want. Now it's too crowded to write my answer in that little space. Isn't that sad? But I know at this point, all I have to do is multiply all these numbers. So my final answer can be 180, that number, times 12. And look, I can write a shortcut, 12 to the third power. And now I can write this as an exponent, inches cubed. I don't have to write those all out here. This is the neatest, most concise way to write the answer to this problem, and I find it highly satisfying. Now, when you go to the instructions or the solutions manual, John may have 180 times 12 times 12 times 12. He may write those out separately. Yours is correct. If you use the exponent just to simplify writing that, that's perfectly fine. Sometimes John will put the ones in as well. You might create a fraction and put 1 times 1 times 1. You just have to remind yourself, yeah, you can show the ones if you want to, but dividing by 1 doesn't change anything. So if you ignore those, it's fine. This is the way I like to see the answer, neat and concise. I like to see all your work up here. I wouldn't be happy if you didn't show the boxes with the ones in them, but I don't need you to show that in the answer. Okay, one more, and then we're done. In this problem, John would like us to use 6 unit multipliers, to convert 800 cubic centimeters. Okay, so we're starting with 800, and I'm gonna go down this time because I think I'm gonna need a lot of room, right? Cubic centimeters to cubic feet. Okay, so I see right away we're gonna jump the chasm between metrics and English. And he tells me I need to use 6 multipliers. So I'm going to draw a massive set of them. Okay. So I know that these 3 are all going to be the same. And then there's going to be a change. And then these 3 are all going to be the same. Right? Because we're computing volume and we have 3 dimensions, that means I have to use each of the same multipliers 3 times. If he tells me I need 6, then that means I'm going to converting in 2 steps, and each step will require 3 boxes. All right, so that just helps me know how to organize my space. He's helping us. All right, I know that the portal to get from metric to English is at between centimeters and inches. So I know I'm going to have to do that first. Then once I'm in inches, okay, then I can get directly to feet. Right, so I plan my map out down here. This is my plan for how I'm going to get there. So let's go in and do the first one. Centimeters to inches, I know I'm going to want centimeters on the bottom. And even though it doesn't look like it, this is all in the numerator, right? Okay, that means inches are going to be up here. What's bigger, an inch or a centimeter? An inch. And then my centimeters are 2.54, right? Oh, now I can't fit that in very well. I'm going to have to squeeze a little. And I'm going to address this in just a minute, how to get around making this big mess. Okay, centimeters can cancel. And now I've got a problem that's stated in inches. I want it in feet, so I know I'm not done yet. Okay, this step I want to go from inches to feet. That sounds about right, because I'm in inches, and now I want to go to feet. So I'm going to need the inches down here, so they'll cancel. And then that means I'll have my feet up here, which sounds weird. Okay, what's bigger, a foot or an inch? A foot, a foot, a foot. How many inches are in a foot? Pay attention to the questions that I ask myself, because in your homework, you have to ask the same questions, right? Where do I want my starting unit? Which unit do I want on the bottom? Which of the 2 units is bigger? That one gets the 1. And then what's that special number that links the new unit to the old unit? Okay, now I can cancel. Okay, now all these inches cancel against each other. And I'm left in feet. That's exactly where I want to be. Okay, now all I need to do is simplify this answer. Again, what I would do is I would write 800 Now look, ones all the way across the board. I'm not gonna copy those. We don't need those. John might show it like this. You don't need to do that. On the bottom, look, we have 2.54 3 times, and then we have 12 3 times. I'm gonna leave those in there this time just to show that they don't hurt you, but I don't like those. And then our final answer is gonna be in feet cubed. Right? John sometimes uses parentheses instead of dots to show this. Again, that's just a style preference. If you like to use parentheses, go ahead. I do sometimes. I like dots though to show the multiplication because they're faster to write than putting parentheses around everything. Okay, now, I don't think I want to give you the shortcut yet. I want to wait till we get to another lesson, and I'll show you a different way that we can write these so that we don't have to write so much. But for now, just go ahead and write out all the boxes like that, and we'll deal with shortcuts later. All right, that is the end of lesson 53. I enjoyed it very much, and I hope you did too. Thank you. Goodbye.